Okay, welcome everyone to the Air Sea Fluxes from Space webinar series. Today we have Elisabeth Rémy from Mercator Ocean International. She'll be talking about assimilating simulated Odyssey surface current observations in the Mercator Ocean Global System. So take it away, Elisabeth.
So good morning and good afternoon, everyone. So most of the content of this talk was produced by Isabelle Mirouze with the help of the Mercator Ocean teams with running the monitoring and forecasting system, the data assimilation system. So here, the main objective of the data assimilation experiment we were running with our global 1/4 of a degree system with the Odysea simulated observations is to assess their impact, assessing the impact of surface current data on a global ocean data assimilation systems. And when they are added to the present observation that are the in situ, SST, and SLA observations, we also wanted to look at the complementarity with nadir altimetry observations. And we begin to look also at the sensitivity of the performance of the results to the orbit and the level of errors. So those experiments also allows us to look at the weaknesses that we can have in our system and to identify system evolution that would improve the benefit of surface current data assimilation. So the result I'm showing here with the Odysea observations are taking advantage of a previous study we've done with the scheme data. So the approach we are using, for those who are not familiar with them, are called OSSE, for Observing System Simulation Experiments. That means that we are simulating the observations from nature, what we call a nature run, so different simulation. And then we can compare when we assimilate those simulated observations, we can compare what we obtain to the nature one, which is supposed to represent the real world. So of course, there are several steps to calibrate those experiments. And here we choose to have a different model configuration, different forcings, and so on, to ensure differences between our kind of simulated ocean and our forecasting system that mimic the difference that exists between the real ocean and our forecast model. So here is the set of experiments we did. So here I will first, on the first part of the talk, to the difference between an experiment assimilating the present observations, so I mean SST, temperature and salinity profile, sea ice observations, and SSH. And then I will look at the last one when we add the U and V observations simulated as for the Odysea mission. So I should say that we thin the observations because we have a 1/4 of a degree, quite a low resolution model. So the density would be too high. So we may improve in the future the way we used with two super ops here, but here are just thinning methods. So in terms of simulating the Odysea observations and the error, it is based on the GPL simulator, and which was also slightly modified by Lucille Gauthier at ODL. So the observation values are extracted from a global 1/12 of a degree simulation, and the errors are really simulated with the Odysea simulator, and the figures are highlighting an example for one source. So you have the error for U on the left, in the middle for V, and then the wind. So we can clearly see the increased level of error in the center and at the edge of the source, but in fact it was removed here. And also we can see that the errors are higher for the U component and much higher when the wind is really low. But I should say that so those observation errors depend on the position of the observation within the throat and the wing, as we've seen, that it's random up to now. So here, an overlook of the improvement when we assimilate the Odysea observations on top of the others, including the altimetry. So everything in blue means there are an improvement when we assimilate the U and V components, and red degradation. So we can see that there's an overall benefit of having the Odysea observation assimilated, and the stronger one, especially at the equator for U and V. We see larger improvement over the globe for V, and in temperature, there's an overall improvement, but there are areas also, there are degradation and improvement with clearly improvement in the Pacific, most in the eastern part. And for the salinity, the improvements are really strong in the weaver plums. So if we now look at if those improvements that we've seen before in the analysis are retained in the forecast. So here it's time series over our 7-day forecast of the run means the error we have compared to the nature run, depending of the two OSSE. So in orange, we have the one with the SSH, and in blue, it's when we assimilate the surface velocity in addition. So we can see that overall for the global statistics and at the equator and also the Gulf Stream, the information is retained in the forecast, and it means a gain of 1 day for the global statistics. And it's really at the equator, as we've seen in the maps, that the improvements are the highest, and they are kept over the 7 days. And in the Gulf Stream, the improvement is there, but it's smaller, but it's still kept over the 7 days. So somehow it means that what we corrected in our simulation seems to be coherent, and so it can be retained in these 1/4 of a degree simulations. So I will now show the complementarity with altimetry. To do that, we run an additional experiment. So there's what was called control or SSH with the present observations. Then when only the Odysea observation are assimilated but without altimetry, and then both are assimilated. So I should say that here we simulated 5 nadir altimeters. So it's quite tricky, so I will go. So we compare how well the estimates from those different OSSE performed compared to the nature run. So we look at how the errors are smaller or bigger depending on which OSSE we look at. So in the first row, we compared the case with only velocities assimilated and only SSH. So in blue, when the velocities perform better, and then in red, it's the opposite. So we can see that when we look at the zonal velocities, they are improved by the assimilation of UV, but they are better estimated when the SSH is assimilated. For U, for the meridional component, we can see that it's better performed when the surface velocity are assimilated than the SSH. So, and then the panel below, we compare the simulations where U and the velocity and SSH are assimilated compared to only altimetry. So what we can see is that adding on top of the altimetry, the velocity observations will improve U and V everywhere. So with largest improvement at the equator, and again, it's more the meridional component that is really performed better, and less improvement for U. So here it's the time series associated with the experiment I've shown just before, just to confirm what we've seen before. So over the time of, so it's less than a year, because we removed the first months due to it's kind of a setup for those experiments. So the hypothesis for these differences between U and V components, there are 2 possibilities, we think. It's the altimetry track orientations that really helps to constrain the perpendicular component, but there is also the fact that there's higher error on zonal currents for Odysea. So we don't know how those reasons are contributing to these overall results. So we also, since we are assimilating surface observations and surface velocity, we want to know what if we can see improvement, or it may happen degradation, when we project this information from the surface on the water column. So it's the vertical profile of the errors in colors for the different OSSC as before. So what we can say is, I begin with the meridional velocities. So they are improved compared to SSH with the only velocity assimilated, and then further improved when both are assimilated. But as before, we found that to project the for U, the zonal component, there's really a need to have also the SSH to really well project the information from the surface to the depths. And if we have only the Odysea observations, we tend to degrade the velocities at depths compared to only SSH. So those statistics are for the global, and we also looked at different regions. So here are just two examples, really to highlight that the way the system behaves can differ depending on the region and the dynamic. So at the equator, since it's really the geostrophic part cannot be well constrained by altimetry, we can see that the UNV and UV and SSH perform better than SSH only. And in the North Atlantic, we found the results that we had before. It was an example of a western boundary current. But what is nice is that still the improvement goes quite deep when we assimilate both SSH and UV. So now we also looked at other variables, the temperature, the SST, and the sea surface salinity, to see if they are changed, improved, or degraded, depending of which observation I used to constrain them. So I go directly to when we add the U and V components, the U and V on top of the SSH. So it's the salinity is improved in the river plums and in the tropics. It's also true for the temperature. And for from the top panel, sorry, I'll be back. If we have only SSH versus only U and V, we can see that there are areas of degradation and there are areas of improvement depending of which variables. So it's really when adding both that we get more improvement. And I should, yeah, that's fine. So, and we also looked at how the performance at depth for temperature and salinity are changed. So there are slight changes and the better results are obtained where both data sets are assimilated. For salinity on global statistics, it's quite small. So those changes are fine, but they are still quite small. So now we looked at the SSH. So at the top, it's really highlighting that the SSH, of course, is better constraining the SSH variable in the analysis. And at the bottom, we can see that if we add on top of the SSH UV, then it improves further the SSH estimate, which is quite interesting. And the improvement are the strongest from the time series we see on the right on the equator, but there are also improvements in the Gulf Stream area. So here it's a kind of table to summarize in different regions and for different variables the RMS statistic, the improvement and degradation between the assimilating only velocities and only SSH. So in green, it's what is improved when assimilating the Odysea observations, and it highlights that it's improving the currents, and especially at the equator, and also the SST at the equator. And if we now look at the same kind of table, but comparing when we add SSH and velocities compared to SSH, we can see that everything is green. When it's a light color, it means it's not statistically relevant. So we see that even if in some region as the equator and variables, the improvements are quite strong. And then, but even on SSH and T and S, we can see slight improvements, so which is fine. So we did another kind of validation. It's really looking at drift, since we think that the assimilating the surface velocity should improve these fields, and it could have an impact on many applications linked to drift of object, but also algae and so on. So what we did is there are particles that were uniformly positioned in the nature run and in the different OSSE to look at how they are drifting over 6 days. And we compare the position they reach after those 6 days in the OSSE and in our reality, so the nature run. And we also looked at diagnostic, which is called the Liu skill scores. So in that case, the errors is weighted by the travel distance. So it means if it doesn't, it looks at the relative error compared to the travel distance by the particles. And another benefit we found with such Lagrangian diagnostic is that it tends to integrate in time the errors along the path. So sometimes looking at the fields themselves, you cannot see so much, but looking at the drift after several days, you can really highlight some regions that have problems or are improved and the opposite. So here the comparison is done with the when only SSH is assimilated and then when the UV is added. So on the left, you have the difference in the position after 6 drift day. So we can see that the highest values in kilometers are in storm currents, so tropics, ACC, and western boundary current. And at the bottom left, we can see that those distances are reduced. So the colors are more closer, yellow and white, when the velocities are added. And on the right is this Liu index. So it's sorry. So when it's blue, it means it's quite good, and when it's red, it means that the travel lengths and error are similar. But we can see that having the Odysea observations on top of the usual observations still bring improvement quite everywhere. So, and the last set of experiments that were done last year was to look at the sensitivity to the orbit. So we tried the orbit, which is called the F configuration, with around 60 kilometers orbit and the 80 kilometers orbit. And then the design of the experiment was done such way that only the orbit, the sampling has an influence, but the error is not changed. And then there is a second set of experiments, which is using a higher level of errors compared to the low error that were used here. So here it's for the orbit. So the color scale is divided by 2 compared to before. So we see an impact, and it depends on the regions, but it's quite small, I would say. And the orbit at 800 kilometers seems to perform slightly better at the equator, but results are mixed elsewhere. And Odysea for the F so 600 kilometers height, slightly perform better locally. So here it's the same kind of diagnostic, but between when different error levels are used. And so I should mention from the, for the orbit, we can see that differences are found at slightly higher level at the equator. So we should go further to explain, to understand why. And here it's more completely uniformly differences, and that could be improvement or degradation, but slightly when we change the errors. So as a conclusion, assimilating the satellite surface velocity data improves all variables, the root mean square error. So the currents are improved the most at the equator, with more than 20% of improvements. The SST-RMS is improved, especially in the Pacific, Equatorial Pacific, in the Niño boxes that could have an interest for ENSO prediction. The salinity is clearly strongly improved in the river plums, so thanks to a better advection, the currents in those regions. And the satellite surface velocity observation and SSS observations are clearly complementary. And we also seen that the benefit we have for the analysis persist over 7-day forecasts. So we think that those results, there can be some improvements that we could expect with better data assimilation tunings. And I should say that the results I just presented are from OSSE, so somehow on a simulated world, and they are highly dependent on the data assimilation we are using. So here, the nature run we use to simulate the observation has no tidal forcing and is not coupled with waves. And there are other centers that run or will run OSSE for surface velocities with their own system. So for example, there was the Met Office, and Jenny will present the results next week. And there are also the NRL, which is currently running OSSE for Odysea in the Gulf of Mexico. And we will have the opportunity to compare our results because it's really regional higher resolution, but it seems that they have already kind of similar results, difference between U and V. And the fact of having multi-system experiment really can help to mitigate the result dependency to the system design. So I think we have plenty of perspectives and challenges, so it's more kind of a long list. So really the short-term objectives is to analyze further the velocity components that are improved, geostrophy, ageostrophy, and to better understand also the complementarity with altimetry. We also need to test the sensitivity of our analysis to systematic errors. There are methods in the type simulations that exist, even if it's not so easy to use, but they exist, so we should try that. And in terms of midterm objectives, we've seen that we would like to improve the way the information from the surface is projected at depth through vertical covariance. And we think we expand too much on the vertical, the information at depth, especially at the equator, and we may restrain this projection of surface velocity in the to the mixed layer. There's also the question of how to deal with the really high density of observations compared to the model effective resolution. So here we use the thinning, but we should go for super robbing or filtering to better take into account correlations errors, and so how the signal and errors could be correlated. And there's also here we used a 7-day assimilation window, which is kind of unusual today because most of the operational systems are closer to 1-day window. And there's the question of how to deal with the sub-daily variability, with the near inertial oscillation, and so on. So, for example, Met Office tried to have a specific way of correcting the model over a day to take into account the near inertial oscillations. And then on long-term perspective, here we really assimilated the U and V component as if they were completely independent. So one thing is to assimilate radial velocities, but which may be difficult, but it will avoid the correlation between U and V, or to take care of that even if we are still assimilating vector components. And of course, since Odysea will have the opportunity to have wind and current collocated observations, that's really something that could help, because here we don't change the wind, even if we change the current. So we may try a really simple way by correcting the wind on a linear fashion, or really to have an inclusion of the wind in the control vector when assimilating the surface velocities. And of course, in the so for those who are running coupled systems, there's the opportunity of assimilating wind and current observations, but that's also an entire challenge. So that's it. So if any questions?
Well, thank you. I see that there's a question in the chat from Eric Hacker. Eric, do you want to ask your question?
Sure, I'll speak it out loud. I was curious. First off, Elisabeth, very nice talk. I liked it a lot. How does the Odysea simulator create the observation error for U and V?
So to be honest, I still don't know the details of the simulator. It's really a function. It's creating a random error, which is the function of the wind at the observation location and also the position on the track. So is it answering or you had some other ideas?
Okay, so you said it's the position of on the track and also the local wind field.
Yeah, it's really the local wind field. We can see really much higher errors in a low wind location. And also, to be honest, for the position on the SWOT, it's a complex function. And you can see some bend that are parallel to the source. So, okay, Gerald may help. So I don't know.
Okay.
I'm just chiming in to say that this was not done by Mercator. This was done in collaboration with the project. And the simulator actually is an extension of what JPL has developed, and Alex in particular. It was updated with the error budget that we have, and it is a very simplified simulation of the radar and ground processing. It will essentially simulate the fact that you have a directional measurement, so the ability to reconstruct a vector in the along track or across track direction or in the north and east component is variable depending on the geometry. So all of this is accounted for according to what the project knows as of today, and we are simulating only the random component of the error, which is by far the largest. Since we are talking about tens of centimeters of errors for the higher resolutions. And when there is little to no wind, the error will skyrocket to meters per second. So all of this was accounted for to the best of our ability in a phase A.
So can I follow up with a question? Is the local eddy structure in the ocean considered at all from the simulator? Like if it's flying over the
At the
center
moment,
of the gyre might be different than if it's flying over the Gulf Stream, for example.
Yes and no. A fraction of it is accounted for because the simulations use the wind, which has a geographical distribution that is accounted for. So that part is taken into account. In the regions where winds are frequently low, you will see that the random error will increase. However, in the specific simulations, the correlation between the atmosphere and the ocean is not accounted for. So at smaller scales, we're probably missing various effects that are not in the simulation used by Mercator. Last but not least, we expect to have some non-random part of the errors that are not accounted for at the moment in the current simulations. And that is something that we want to improve upon.
Okay, thank you. Nice.
And it's worth noting that the baseline simulator is available on GitHub. You can get to it from the Odyssey website. So if you want to play with it, it's available. Other questions?
Hi, Sarah. May I ask a question?
Yeah, Tony, go ahead.
Elisabeth, thank you very much. It's very nice work and very nice presentation. I have a question about the data assimilated, the choice of a data assimilated. So you could assimilate all the data regardless of the uncertainty by accounting for the uncertainty of every data point that you assimilate, including those with low wind and those at the edge of the swath, both of which have larger error. Or one could choose to limit the assimilation to the surface current under stronger wind situation, say higher than 5 meters per second, higher than 7 meters per second, for example, which reduce your data volume, but better quality surface current observation. And also one could limit the assimilation to the high performance region of the swath, meaning away from the edge and away from the center, where the errors are relatively small. So do you think that with your current assimilation scheme, those two choices will have different results, meaning that assimilate only high performance surface current observation, a lot less data, versus assimilate everything, including those have large error, whether there will be a difference in impact?
We don't have the answer, but certainly we will try it, because right now we know, you're right, I did not mention that in the short-term objectives. Really, since we have the wind, we can use that to mask on our side, to decide to mask the data when the wind is quite really low, or as you said, to keep only the high performance areas. So right now we are just increasing a lot the error, since it's already high. So I think it should not change so much the results if we consider the wind itself, but high performance areas we should check. Yeah.
Mm-hmm. So,
yeah, we should check the different strategy to somehow not assimilating data in the region we think the errors are too high.
Right. So currently the swath location dependence of the error is considered, right? Meaning that you have uncertainty on the outside edge of the swath that are large. You don't inflate the error for the whole thing. You still consider relatively smaller error in
no,
the
we consider
area.
No, the way it was done, in fact, I don't have all the detail, and I don't. Isabelle is here. No, since we did not had she tried just to mimic somehow the error, but now we got the kind of function to use in order to really have this increase at the edge and at the center, the analytical function, and not just using what we get from the files, the simulated error. But I don't know if Isabelle can add something, but we will look and discuss more carefully this aspect.
Yeah, thank you.
Isabelle, did you want to say something?
You can't hear me. Right?
Now we can.
Okay. No, it's just to say that the way we have done things is not very correct now. So we intend to reduce some of the runs with after just studying a little bit more this error. But even now, the instrument error is we take into account the place in the swath anyway. So just to mention that.
Okay, thank you, Isabelle. So that means by assimilating data in the high performance region of the swath, it's probably not going to make much of difference because you already accounted for that swath location dependent error. Right?
Yeah, I don't think it will make a huge error, but we need to test that anyway and do something a little bit better. And I think that, yes, you mentioned that trying to limit the data if we have enough wind and that kind of things. I think that's something we will add anyway, because when the wind is really, really slow, well, the error is so huge that it doesn't make sense to assimilate it anyway.
Right. Thank you.
Other questions? And maybe I can ask, you've shown these comparisons against 3 different assimilation cases, but presumably there's sort of a worse than that case where you only assimilate 1 nadir altimeter or you only have a scattering of Argo data. How much improvement is there just from assimilating something? The suite of nadir altimeters versus having nothing to assimilate? And how does the addition of the second satellite compare with the going from nothing to one of these sets of products you're looking at?
Okay, if I get your question compared to
so
yeah,
I think what I saw is that nadir altimetry, the set of nadir altimeters, and the UV velocity from an Odysea-like instrument for some variables showed comparable impacts. And so I guess I'm wondering how bad would it be if you were reduced to only 1 nadir altimeter or no nadir altimeters, but a few in situ observations?
Yeah.
So what's the baseline gain?
Yeah, I think there are 2 things. We may see further larger improvement for U and V, since we will not have the information from the SSH. But at the opposite, I would guess that not having in situ observations will pose a problem in terms of projecting the information, even for the SSH. So then we need those temperature and salinity data to have the vertical structure of the ocean that helps to project the altimetry. And then, so it's kind of, yeah, cascading effect and complementarity between the ocean interior and for the surface. And then in terms of kind of percentage or kind of measure, if we have only 1 nadir versus 5 nadir altimeters, we did some studies, but I don't know here. Yeah,
it wasn't part of the study, and this was really nice.
Yeah, yeah.
So if there are no other hands, I'll ask one other question. You're running a model that's a 1/4 degree resolution. So I'm guessing the effective resolution is sort of a degree, but I don't know. What do you think it is?
So the effect, yeah, it can be. So what is being said is the effective resolution can be between 5 and 7 grid cell size. So which means it's probably more than 100 kilometers. So of course it depends, since the grid it will be larger at the equator and smaller close to the polar regions. Yeah, but we choose really this 1/4 of a degree global systems because it's much easier to begin with, to run single experiment and so on. And since we have a lot of development, test, and things to understand, we begin with that. But we know that having a 1/12 of a degree, would be richer, but we also need a nature run at higher resolution and adding complexity. So that was a choice.
Yeah, I don't want to dispute what you've done. I'm just curious about
Yeah.
thinking about the dimensions of that, because what that means is that you're really doing the assimilation at scales that are probably dominated by geostrophic motions or balanced motions. And you might imagine that things would change if you were able to go to smaller scales, that there would be different types of motions that would come to the fore, and that would shift the balance. And I don't know if you've thought much about what that might actually look like. It's a very hypothetical question at the moment. As you say, it's not very practical.
No, I fully agree. In terms of spectrum, here we can explore only really a part, and maybe not the part where we would see more added values. And but that's why we would like to look at the geostrophy and that geostrophy components and the velocity and widgets already to have a kind of guess, even if it will not be at those scales. Geostrophy may be quite small, but still, we would like to look at that to further some ideas at least.
Yeah. Thank you. Are there other questions? Tony has his hand up.
Yeah, thanks. Another question is about the vertical error covariance, how the velocity, horizontal velocity is propagating down to subsurface velocity. And in your assimilation scheme, that is calculated from the nature runs model field, is it correct?
So in our systems, the covariance are based, it's really, there is no limitation on the vertical. It's a 3D localized, 3D local kind of EOF of a model simulation. And to be honest, I don't remember, not from the nature world, that's for sure. So it's coming from a previous simulation to have the kind of anomalies that can exist. And there's no limitation on depth. It's considered as a kind of a water column. So it's a 3D, but localized around the grid cell on the horizontal.
And it's some kind of decomposition into vertical modes.
Yes.
I see. And is the UK metaphysics system handling the vertical error covariance the same way?
No, absolutely not. No, they are using the 3D VAR approach with this equilibrium between the different components. So as Anthony Weaver developed, so if it means something, so it's really looking at cascading from TS and then geostrophy, and they limit the influence of the surface data in the mixed layer depths. So Isabelle Mirouze may know also because she was running the later version of it. But yeah, it's really different.
I see. And we don't know how the Naval Research Lab system is handling that. You probably do?
I don't know.
Okay. Yeah.
I have to ask them.
Right. That seems to be a key opportunity there to cross-compare different systems to see how the information is propagating down to the vertical direction to influence the subsurface ocean.
And how the combination of the different observations are impacting at depth, the cross covariance somehow.
Right. The advantages of those different methods of handling vertical error covariance may be scale sensitive or regionally dependent, tropics versus mid-latitude where geostrophy is dominant.
And Isabelle wanted to look at our codes and if it's a possibility, if there is a possibility of vertical localization, but it seems to be tricky the way it's written.
Yeah, just to explain for the hypothesis, what they do is they have two operators. One operator is considers a balance between, so that's what Elisabeth explained. And there is also an operator for the correlation, the a special correlation for each of the variables that is based on the different equation. So that's why in the vertical, you can just, define what is the length scale you want. And so, for example, for TNS,
Isabelle, I think if you could be closer to your mic, that might help.
So for the vertical, what they do, for example, for TNS is that they will choose a length scale that depends on the mixed layer depth. So in the mixed layer depth, and then after that will just depend on the grid, because you need to have at least one mesh for the different equation to work well. So that's really, really different. So they have a kind of localization.
Thanks.
Thank you.
That was, we've seen the consequences with the scheme like the scheme OSSE somehow. They had the same we had the similar results overall when looking at the surface velocity improvements in the analysis and the forecasts, but then looking at depths and other variables, it was really different.
Can I ask about the salinity results? Because I thought those were very surprising. Did you expect that there would be such a strong improvement for salinity?
No, but when we've seen that, I remember that discussion about the sea surface salinity satellite observations, when they compare with the models, and trying to understand the patterns of the SSS, they understand that it's mostly impacted by Ekman, the Ekman wind.
Okay.
So there was this hypothesis of a very strong influence of really the Ekman velocities in the way the river plums are drifting in the ocean. And when we did some assimilation experiment and also looking at the differences in our system, we found those regions. So yeah, maybe not so surprising.
Yeah, not part of the folklore we come to expect, but fascinating. And as you say, probably what we would have if we'd really thought about it. Okay.
One more
Anything else?
question. I have one more question.
Yeah.
Sorry.
Tony.
The 7-day data assimilation window, does that mean, what does that mean for the constraint of variability that have time scale shorter than 7 days? Is there a constraint on shorter than 7-day variability in your assimilation system?
No. It's
Okay.
really the model itself, because
I
we are
see.
so incremental analysis is update, and the way it is done, it's really over the 7 days. So I'm
more like an averaging.
I'm not completely right, since the analysis is done using the innovation once, but then we used EOF that are respective for each day. So which means they can put some daily variability, but I won't say that we control things that are below 7 days. Can help, but yeah. And this window should be reduced in the future, and their way to, but yeah, basically it's 7 days.
Right. So if you do that, say daily assimilation time window, the difference between the SSH run and the UV run might have bigger difference on the shorter time scale, including for the impact on the forecast, just because 7 day, the altimetry constellation can constrain that, but Odyssey can actually do better than 7 days in terms of constraining the variability, right? So on the shorter time scale, the impact of the UMV might be different if you use a daily time window. Just hypothetical or theoretical.
Yeah, I agree.
assumption.
I agree with the idea. Yeah.
And that's related to the transition from unbalanced to balanced motion too, I think.
And so, yeah, at the, as you said, for the spatial scales, it's
Yeah,
true
yeah.
for that.
Well, I don't want to stop anybody if they have questions, but if there are no further questions, let's thank Elisabeth for a really wonderful talk and an engaging discussion. And next week, I think we'll have more on this topic with the UK model, Jennifer Waters.
Thank you, Elisabeth.
Thank you.
Bye-bye.